Okay, all right. I think it's about time we can start now. So let me use my full screen mode. Can you see my desktop?
Yes, Professor.
Okay,
Yes,
all right. Okay, good afternoon, everyone. This is Dr. Carl Ng. I'm the co-chair of this online forum. This is a online event, the Quantum Science and Computing Free Online Forum. I am one of the organizer of this event with Professor K.T. Huang and Mr. Alex Sun. We have added a website for this event. The URL address for this event is https://quantum.asia.edu.tw. If you follow this link, then you will see this is the home page. And then please click on this the hyperlink. This will bring you to a new web page. Over this website, we have a brief description about this quantum forum. You can also use this link to sign up. Right. So after you follow this link, this will carry you forward to this Google form. Okay. So then scroll down the page and then fill up your personal detail. Just sign up once. No need to do it again. Just do it once. Another thing about this is we also welcome your volunteer to sign up for presentation. So please follow this link, and then at the bottom of this page, you can download the form and then fill in the form and email this to this Gmail address, qphysics.qcom@gmail.com for approval. Now, subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 5 days after the presentation. So we have organized a lecture series titled Quantum Machine Learning and its Biomedical and Physical Application. This is the fourth event, and there will be another one coming up at April 12th next week. So today we are very pleased to have Dr. Andra. The title of his talk is Autoencoder, Quantum Encoder, QGAN, and Demo. Dr. Andra is a postdoc researcher at the Research Center for AI and Cybersecurity Indonesia. He graduated from the Technology Institute of Sepuluh, Nopimava in Surabaya with a bachelor degree in computer science in 2015. He later entered the International Joint Education Program, which allowed him to complete his master's degree in the Department of Computer Science and Electrical Engineering at Kumamoto University in Japan. He completed his master's degree in 2018 and pursued a doctorate at the same campus. He completed his study in 2021 and received a PhD in the human and environmental informatics. His research interests shift from year to year, although his primary concentration is on speech processing, digital signal processing, and machine learning. He has been involved in several organizations such as the Acoustic Society of Japan, the IEEE student chapter in Kyushu, and the IEEE Geoscience and Remote Sensing Symposium. So for that, let's welcome Dr. Andra. So let me pass my microphone to him.
Yeah, thank you very much, Professor, for the kind introduction. Before we start, maybe I will share my screen first, so we can get ready for the presentation. Okay, could everyone see my screen now?
Yes.
Okay. All right. Thank you very much, and I'm really glad to be here today. Thank you very much for the opportunity to share a little bit of presentation and maybe our work in our group. Maybe Professor has introduced about me earlier. My name is Muhammad Bagus Andra, and I'm currently doing my postdoctoral research under the guidance of Professor Hilman F. Pardede in the Research Center for AI and Cybersecurity in Indonesia. We are actually an organization called BRIN, which is uh, the center of the all research in Indonesia. So for today, I would like to share about my postdoctoral work, maybe for this around for 1 year. I get the opportunity to take on a topic that is honestly really new to me. It is about quantum computing using machine learning. As we all know, this field is quite new and really a lot of possibilities and potential. I'm actually quite not unsure for the first time when I took this topic whether I will could maybe study about the topic and doing the research, but the research of the quantum computing is actually really interesting in my opinion. Maybe there's a lot of things I still don't understand. So if there's some error in my presentation, please feel free to correct or maybe give a feedback. Thank you very much.
Yes. Yes,
So
Dr. Andra.
yeah.
Yes, could you mind use the full screen mode
Oh,
for
okay.
your PowerPoint? Yes.
Sorry. Uh, you couldn't you see my screen?
Yes.
Uh, Sorry. Wait a minute. Okay. How about now, Professor?
Can you do that one more time? Yeah, I
Yeah.
can see your PowerPoint. Okay,
Oh,
yeah,
okay.
now it's good. Now
All
it's
right.
in the full screen mode. Yes, good. Thank you.
Okay, sorry for the trouble. So yeah, we'll continue for the topic of my talk today. I'm currently researching about quantum and autoencoder and generative AI using the quantum technology. So in the form of a generative adversarial network. In this particular research, we are using medical image, specifically cancer image, as our domain or subject of study. So let me begin the presentation. So first and foremost, maybe we'll talk a bit about medical image processing. So the medical image processing is already quite advanced field, and recently it's been boosted and really improved by the introduction of deep learning. And as you know, there's a lot of GPU computation power nowadays. Like we could do a lot of computation in the consumer hardware, such as NVIDIA GPU, and it's really helping this field of research with its advance and progression. So, quoting from some research paper, actually in the field of medical image processing, we could generally divide the research or the process in two parts. So the first part is the acquisition and reconstruction of the image itself. This involves the object of the image itself. That's a medical object, such as, for example, in this case, is a brain. So, human brain. We want to make an image out of it. We are using MRI system in this case, and by using the case space and reconstruction, we could get the medical image that is the like the image of the brain of someone's or subject that has maybe a disease or tumor. And the second part is image processing and analysis. So we already gathered the medical image from the first step. Now the question is what we do with that image. So this is has a lot of potential, of course. For example, in this case, if the patient has a brain tumor, we could do image analysis using that medical image, and we could do some segmentation or maybe classification to automatically detect whether that person is having a brain tumor or not. So in our group specifically, we are focusing on the second part. That is, we use the available data set or medical image, and we do a processing and analysis, and we are doing some machine learning method to do classification or segmentation depending on the subject or the image itself. So as for the recent years, we could see that CNN is being used as a really popular method or a main method in many medical image analysis. This is quite given because the capability of CNN by representing the image in the 2D space, which still retains its positional information or spatial information, we could detect and we could do a lot of processing in using that architecture compared to maybe usual usual neural network, because by preserving the spatial information in this regard, it will represent the image or the data more accurately, because as we know, the 2D data of image is really affected by its spatial, because if we, for example, we shuffle or we swap the pixel in the image, it could be interpreted as a totally different image. So this is really important, and maybe this is one of the reasons why CNN is used as a main method in the recent medical analysis. Now, in this doing this image processing, there's a lot of challenges that arise, especially from the domain of medical image. There's some problem or some challenge that is unique to that domain. So here I took this figure from the paper by Jürgen Weiss. He explained about the four challenges in medical image analysis, and and in the recent year or in the trending topic is the four problem, that is anatomical models, algorithms for heterogeneous data, efficient ground truth generation, and adaptable image analysis technologies. So from these four problems that arise, we are interested to tackle the third one, that is efficient ground truth generation. It is concerned about how the data set retains its quality, how we could process and how we could verify that the data and the ground truth is accurate. And so moving forward, we will focus on this problem in this study. So more specifically, in that domain problem, we have two objective or two topic as our main focus. So the first one is high dimensionality. As you know, the medical image is usually gathered or generated by a specialized device or method, which usually results in a really high resolution or high dimensionality data. There's also one example is about DNA sequence or gene sequence. It also have a really high dimensional. So we are interested in how we could reduce this high dimensionality, and we could simplify the computation by picking just the important important properties or important category in this data, and it will lead to much more faster computation and also a simpler algorithm, and it will save a computing research in the long term. And to tackle this problem, we are trying the method of quantum autoencoder, which we will explore later. The second one is the problem of class imbalance. So because the medical data, maybe in this case, usually like a cancer data or something that is related with disease or anomaly, usually the distribution of the data is in imbalance because there's a much more small sample of the disease or maybe the positive cases of that anomaly compared to the negative one. So there's usually many data of a healthy people compared to the one with that symptom. So this led to a lot of issues such as poor performance in the classification model and also making the data, the distribution of the data itself skew to some classes, which make the model overfit or maybe underfit, depends on the data itself. So in this case, we are trying to do data augmentation for that data set using the quantum GAN method. So okay, first we will see about the first problem that I mentioned earlier about dimensionality reduction. So I would like to begin with the concept of the dimensionality reduction itself. So the purpose or the concept of this method is we are trying to reduce the number of features that describe some data or data sets. So as I said earlier, because uh, medical data usually have a lot of row, have a lot of features, maybe could span to like hundred thousands of features. We would like to reduce that to a much more smaller subset of the feature that still could represent that data accurately. So maybe there's some of the data that is not really important, feature that is not really important, and we could cut out that we could still use the remaining data for the machine learning purpose, such as classification. And in generally, there's a two methods for this. There is a reduction and extraction. So the reduction itself is done by simply cutting or throwing some of the features. We are doing feature selection, and there's some method for that, like PCA. We are selecting the most important data or feature in that data set, and we could erase the rest, and that will significantly reduce the space or feature of the dataset. The second one is extraction. Extraction is done by transforming the existing feature to the new feature. This is usually called a latent data or latent variable. So we transform those kind of feature to a much more lower dimensional feature, but still could retain the properties of the data itself. So this is two different approach, but still the purpose is almost the same. And for the dimensional reduction, there's several popular method. Maybe the most common one is PCA, principal component analysis, and maybe another one is linear discriminant analysis. Now, this is maybe a visualization of how we could reduce the dimensionality. So, excuse me for a bit. So, for example, we have this feature space, and we could encode or reduce the feature itself by trying to find the projection or the point in this space, which is by calculating the distance, it is much closer to the original. So, for example, here we have feature point A with two coordinates, and we could encode it to the one dimension from two dimension by calculating the distance, and later we could decode it back into the two-dimensional space. But as you can see, it is not perfectly recovered. So this is an approximation of the original data, which still represents the data itself, albeit there's some kind of variation or maybe some kind of difference. So this kind of method is really important in reducing the data set, so it could still retain the features and there's a minimal information loss. Now we look at autoencoder. Um, from the previous definition, we could explain, or we could uh, understand autoencoder as a system that could map or could transform the initial data from space of r to the power of n to the much more smaller latent variable. In this case, is the uh, r to the power n with r to the power of m, with m is less than n, of course, because we want to a smaller data. And then we could decode it back to the same dimension of the initial data with the space of r to the power of n. Now, the important aspect of this process is we want to have the maximum information when we encode. So here the x is we could retain the most information, and we when we decode it back by using the decoder, we want it to have the minimum reconstruction error. So formally speaking, we could define the function of autoencoder is by the uh, searching the minimum loss of encoding, and after sorry we could search the maximum information of encoding, and then later we could minimize the loss of reconstruction when decoding. So it also defines the reconstruction error measure between the input x and the encoded decoded data. So this is the error definition of the difference between the decoded data and the encoded data. And we could see also that the final decoded data will have the same space as the encoded data. So here's the general concept of autoencoder itself. Now, by using this concept, we could also design autoencoder using a neural network as the encoder and decoder. So because we know we want a model that could reduce the high dimensionality to the lower dimensionality by minimizing the information loss, we could see this encoder and decoder as two separate systems that is consisted of neural network with random parameter. And then we could use a training process to update this parameter inside the encoder and decoder to towards our objective, that is to minimize the loss of the difference between the encoded parts to the decoded parts. So this decoded parts to compared to the encoded parts, and to the encoded parts to the original data. So so the family of encoder here is considered encoders, and the family of D here is considered decoders, is defined by the network architecture and the search of encoder and decoder that minimize the reconstruction error. So by seeing this as a neural network, we could train and update the parameter to get the best result for both of the part of the system. Now let's touch a bit about the optimal encoding, because theoretically, if we, for example, we have like a multi-dimensional data like this, by using the encoder, we could reduce it so small into maybe a point that is a one-dimensional data. But by doing this, we lost a lot of information. So, for example, here, if we there's a four object here: dog, bird, car, and plane, and we try to reduce it to just one feature, we cannot only use, for example, here living as a feature. So the more it gets to the right part, the more it is considered a living being. But as you can see, there's a lot of more difference in this object than living or not living. So here we have a more optimal encoding pattern, or optimal encoding scheme using a 2D plane. We could further divide this into living and flying. So here, for example, we have an airplane is flying and not living. Here is we have a dog is living and not flying, and so on. So there's a trade-off between the size of the encoding and also the information it can pertain or it can keep. So our final objective is we want to reduce the number of the dimension as much as possible, but in the limit while keeping the major part of the data structure and the information. So to train our autoencoder, we wanted to reduce it as much as it could, but in the same time, we don't want to lose a lot of information in doing that. So that's the example of a classical autoencoder. So in RCD, we want to try the how we could apply or we could implement the previous autoencoder in the quantum computing method. So here, actually, we refer heavily to the previous work, which is also working on the quantum encoder by Huang by uh, sorry, I think it's by Huang et al. Uh, so here, what he proposed for quantum autoencoder is we could use quantum circuit to encode a qubit or quantum information. So as you can see here, in the left part, for example, we have quantum information in the red dot. Here we have a 6 qubit, and by using the encoder part, we could reduce this to a 3 qubit. So here the yellow part. So here's the latent variable representation of the quantum information in the yellow dot here. And later, by using the decoder, we could uh, transform it back to the 6 qubit. So for this circuit to embody an autoencoder, so the information contained in some of the input nodes must be discarded. So for example, there's a 6 qubit, we must discard 3 qubits after the encoding. We then prepared another fresh 3 qubit, and by using the parameter train, we could then guide the 3 qubit to generate a newly 6 qubit that represents the initial data. So here, formally defined, the process is the first we prepare an input state C, which contains a qubit of which we wish to compress, and the second one we apply our parameterized circuit. So the circuit already trained and the parameters already updated. We apply that into our input state. It will be acting as an encoder, and it will compress the quantum state. So it in the after compression, it will contain n minus k qubit, where the n is the input and the k is the trace space or the amount of qubit that we want to discard. So as the stated above, we disregard the remaining qubits for the remainder of the circuit. Then as in this bottleneck layer, so here's the latent space is the bottleneck layer. We discard the remaining 3 qubits, and our input state is now compressed. So this is also a figure from the paper by the original author. This is like the overall diagram of the autoencoder in the quantum circuit. So here we use E is of course encoder and D is decoder. We originally have 6 input state in the 6 qubit, and we discard 3 of them by doing the measure here, and we get the 3 remaining as a compressed qubit. This is later then fed into the decoder, and in the final layer, we get back the 6 qubit we originally had. Next one is the detailed component of the quantum autoencoder. So here we can see we are referring to this input part, because actually we could construct the circuit in the decoding part by inversing the circuit of the encoding part. So we could see only in the input circuit, where we have actually you have the input here is 4 qubits, 1, 2, 3, 4, yeah. So the actual input is 4, and we want to reduce it by 2. So we have 2 latent space. This is the will be the result of the compression, 2 qubits, and this is trace space is the 2 qubits that we will discard. And in this case, we still need an additional qubit as a reference space and classical register and auxiliary qubit. So by the design of this input, we still need more qubit than we initially want to input as a process or as a uh, additional qubit for later computation. So here we have several points. We first note that we cannot introduce or disregard qubit in the middle of quantum circuit when implementing autoencoder using QGAN. So this is limitation from the QGAN simulator. And because of that, we must include the reference state as well as our auxiliary qubit, whose role will be described later. And therefore, our input state will consist of our input state, so the first 4, plus the reference space and the classical register and also auxiliary qubit. So this, in the case of implementing with QGAN, this part is needed. Now, after we grasp the concept of the autoencoder and its how it works, we need to know how to train in quantum autoencoder. So here, maybe similar to the classical autoencoder, because it's in the classical autoencoder we use a neural network. Here we also need some parameterized circuit. In this case, usually ANZ circuit is used. That's some kind of circuit that could have updated parameter. So for that, for updating the parameter and training, we need to choose a loss function. So here we use the same loss function described by the original author. How we define the loss function is we let the probability of C, the input state, be a symbol of pure state on n plus k qubits. So this is the state of the our original input. So n here is the latent space, and k is the trace, and the input is the total of both of the qubits. Here we have a subsystem A and B. So A is the encoder and B is the decoder. It's comprised of n and k qubits respectively. And this from this we define a u to the power of p. This is the unitary circuits of quantum circuits that acting or operating on n plus k qubits in some set of parameters defining unitary quantum circuits. So here we have a unitary circuits that have some parameter in it that we need to operate on the input qubits. And using classical learning method, we wish to find the circuit which maximize the average fidelity, which will be defined as the cost function. So here, fidelity is actually the difference between the output of the decoder compared to the original data. So the higher the fidelity, the much more similar between the output of the decoder compared to the original input. So we could maximize that fidelity as a loss function, which defined by this equation. So from the statement above, we could define the parameterized circuit of the quantum, which we use as the autoencoder. But as we know, the parameters is still unknown. How could we maximize the loss function? Is still unknown, and for that we must adjust the value of this parameter. And again, our goal here is maximize the fidelity or the similarity between the input and the output states of the circuit. So we could maximize the fidelity by tuning the parameters in our parameter circuit. But this is can be complicated to determine and may request a large amount of gates. And to work around this, the proposed method is using a swap test to compare the state between the output state and the input state. And by doing this, we could determine the fidelity or the quality of our decoded image. So here's the figure of how the swap test is performed. So first, we have the reference state here, as defined earlier, and we also have trace state here. This two state is compared by using a swap test, and by doing that, we could compute the cost function of the difference between these two states. And after that, we apply an optimization scheme to minimize the cost function from this. And then we update the parameters from the circuit. And then after that, this will be just like a back propagation. We update this, and then the state will be processed again. We get a new trace state and also latent space. We compute cost again, and it will be done many times until our iteration finish. So here it is defined the step formally as we prepare the input state and the reference state. We assume this preparation to be efficient. We evolve the circuit parameter or the encoding unitary circuit, where P is the set of the parameter at given optimization set. Last, we measure the fidelity between trace state and the reference state via swap test. And then the parameter is updated, and this is done again and again.
Yes. Can I ask a question?
Yes, sure, Professor.
Yes. How do we choose the reference state?
Oh, okay. Thanks for the question, Professor. As far as I know, the reference state is like initialized in with a random noise in the example of the implementation, as far as I know. But maybe there's another method to initialize that state, but I haven't read or I haven't know another method. So what we are doing right now is just using the random noise for the reference state. And because it is random, the first iteration will definitely probably result in the bad cost function or bad cost value. And then we update the parameter, and then it will get better in time. So that is the approach for now.
Oh, so the reference state remain the same?
No, the reference state. I think sorry. Yes, yes, Professor. So the reference state is in the implementation that I use right now is the same. So it uses a fixed noise.
Okay. Thank you. Yes.
Yeah. Thank you for the question. So so we'll continue. This is the example of the encoding process. Here we are using the MNIST as the example dataset. So as we know, MNIST uses a 28 by 28 resolution of image, and we reduce it to 8 by 8. So the two reason for this is first, of course, because the computing capacity is really limited, and we are using a simulator for now. This will speed up the computation. And the second one is because we are encoding the data in qubit. As you have known, the qubit is in the state of 2 to the power of n most of the time. So in order to make it easier to represent the image in the qubit, we are transforming it to the pixel that is 2 to the power of n. So for example here, 64-bit is 2 to the power of 6. And this is and for after resize, we fed it into the quantum encoder, and here we see, for example, the result of the encoding. So here, the original size is 64 qubit. Sorry, 64 bit or 6 qubit, and reduce it to 16 bit or 4 qubit. So yeah, quite a reduction in the size. Okay, so next is this is just an illustration for the full version of the encoder, because the previous one we don't touch about the swap test yet. So here is the full representation. We have the input. This is the input state. This is the reference space. This is a classical register. And here we are doing a swap test. And this is the encoder is being updated. And finally, we have measurement. And we have stretch space. This is the qubit that is being discarded. And latent space, which is the qubit we are keeping for the latent variable or the for compressed data. Yeah, this is just the, this is, I take it straight from the code of implementation. Here's what it's look in the Qiskit implementation. If we draw it with the Matplotlib plugin for the Qiskit. So here's the encoder part. This may be similar, this is similar just like in first, because the auxiliary is in this one in the top, this one is in the bottom. Here's the input, here's the swap test, and this is the reference qubit. And this is the full encoder and decoder. Left side is an encoder, right side is decoder. So actually in the code itself, we just use the inverse function of the circuit, so we get the decoder. So here's the full scheme of the autoencoder, which consists of encoder and decoder. Okay, so that the previous one is the application we are testing using MNIST. So in our research, we are trying to apply this method to the medical image. So for our proposed method, here's the overall flow of the data or the method. So first we have the input image. For example, here we have this is a blood cancer data set. We resize this to fit into the qubit space. So ideally, we want this to be resized to the 2 to the power of n. Then we do a pre-process. This is in this case, we try to do a thresholding and edge detection and use it as a feature. And then we do a qubit mapping. We transform this image into input state. Sorry. And after that, we encode it using the quantum autoencoder. And here we get the compressed data. And then what we want to test is what if we use that compressed data in the classifier? Will the classification still perform good with reduced time, or maybe it's really gotten worse and it couldn't be used at all? So here and finally we get the class positive or negative. Yep. And for the dataset, actually we have 3 cancer dataset, and this is I'll just introduce one of them. This one is a histopathologic cancer dataset. This is like the lymph tissue, I think, which is there's a cancer cell in here. So actually this is already labeled, so 0 for benign or negative and 1 for positive. So actually this dataset is, in my opinion, it's quite hard to tell with naked eye, because especially it's not in the medical, not specialized in medical field, because there's like no specialized feature to distinguish between the positive and negative. So yeah, this data set is originally have 220,000 training data, which is quite a lot, but in the this time we only like use 10,000 the dataset, because the time takes so long to training. Yeah, this is the feature extraction, and it maybe I have touched earlier. So first, this is a 19.6 by 96. We resize it to 24 by 24. And then we do this is a thresholding and also control detection. So we tried with this feature and this feature. And this is just the training process for the autoencoder. This one is, I think this one is from the earlier stage of the experiment. We only use 150 iteration. I think in the latest one, we use around 1,000, but that one really takes a long time. So this is the example of the training of the objective function. So as you may see, this is not really a smooth training process. And from the trial and error, there's a lot of things that affect this, especially like learning rate and also the feature we are used to training. So this is really vary a lot from feature to feature. And this is the example of the uh, encoded data. So here we have the raw image, and the right one is the encoded. So actually, the encoded data is maybe one-dimensional, but we force and try to make it two-dimensional to see how it looks, and it really doesn't resemble the original image at all. And this is the decoding example. So the left one is the original data. The right one is the image after we encode and then we decode it. So as you can see, there's still quite a similarity, but some region really have a different intensity in color, and some of the region has this weird color. So this definitely is not a lossless compression, but we could see that it still retains a lot of the feature and maybe a lot of like the shape of the original. And this is the some of our experimental result. This is we calculate the fidelity or the quality between the decoded data and the original data. As I mentioned earlier, we use 3 data set. For the histopathology, it's not really that good. We have the average of 0.8 fidelity, and for blood, this is much more better, 0.991, and skin is a lot better, 0.96. Yeah, this is we assume this is because of the nature of the data. So maybe let me pull back some several slides. So as you can see, this is a histopathology data. The image itself is like quite not random, but it's not having a distinct shape compared to the. This is a blood cancer. So blood cancer is we can see it's have a distinct shape of like a circle, and then there's some nuclei inside it. So this is much more understandable and much more easy to. I think it's much more easy to encode. So this is maybe explain the reason why it is much harder for histopathology data to encode better. And this is next. We want to see the effect of the amount of qubit we reduce. So in the original, we test from 10 qubit to 8 qubit, 12 to 10, and 14 to 12. So here we see the reduction is all 2 qubits, so it's the same reduction, and we could see the trend is almost the same for all feature and all data set. So this is still result in a good fidelity across the dataset. So for 2 qubit, it's still around 0.8 to 0.9 fidelity. But as we move further, we reduce a lot of more qubit. Here we test to reduce 3 qubit. So as you can see, the score is gradually decreasing. So most of them are now only have 0.8 fidelity, except the skin cancer dataset. And more, we see a really tall drop here for 4 qubit reduction. So the originally when we reduce only 2 qubit, we still see 0.9 fidelity. But when we reduce it 4 qubit is really 0.6. So it doesn't, when we decode the image, it doesn't really resemble the original image anymore. And now for the last experiment data, as I have mentioned earlier, we want to try the classification with only encoded image, and we compare to the original image. So the result is quite interesting, in my opinion. So if we use the original image as the feature for the classification, we get the best result in CNN, around 97%. But we only compress, it is reduced, but the reduction itself is maybe in several use cases is still tolerable. So by using the compression, we could reduce the dimension a lot, while the performance itself is not really affected that much. And the second one is the AUC ROC score. This is determining how good the model is in separating two classes. So we also see the same trend where there's a reduction in the ability of the model, but for some cases, it's not really significant. So if our priorities is in the speed, or maybe there's a limit in the space, we could see this being used in some kind of application. Okay, so this is the end of the quantum autoencoder section. So we are going to the next section. This is touching about the second problem that I mentioned in the first slide, or maybe several first slide. So our second focus on the problem is about imbalance class problem. Now, here I want to take an example of some medical image dataset which really had a problem in this imbalance class dataset. So this is the skin cancer dataset, which we also use in the previous experiment. This dataset actually have 6 classes. So there's some kind of class that is actually positive. So for example, here class 1 basal cell carcinoma is positive and melanoma is positive, but the rest is negative. But they are negative in like different way. So for example, I quite forget about the definition, but I think melanocytic navi is just like spot on skin, so it's actually not a disease at all. Well, dermafibroma is like the remaining of a burn skin. So 2 of these is not a cancer, but they are different classes like that. And when we visualize the distribution of the class, so as you can see here, there's a really big discrepancy between each classes. So here we can see the entry classes, which is benign lesion. So this is just a benign spot. It's not it's just a negative class. It really has a lot of data in this data set, but the other data is really small compared to this one. So we thought this might introduce a problem in the model if we train this without any processing. And here our aim is to how we could make the frequency distribution better. And first one of the solution is data augmentation. So it's just an example of one of the most classic and popular augmentation. This is using a rotation on the image to introduce a variation of the data. So usually if the model is trained only on one perspective, it will lead to overfit. So what we do, usually we rotate or we scale or we shift the image, so it will introduce invariance into the model, and the model will not overfit. It will maybe have a less accuracy, but it will have more generalization if we train with a lot of variety data. And how do we do the augmentation itself? There's a simple method such as this. using rotation and scaling. But we thought, how about we try to use GAN, or generative adversarial network, to generate a brand new image that has a similar feature or similar properties from the existing data. So GAN itself is quite a popular generative model that is introduced in 2014 by ENG Goodfellow, a really prominent figure in machine learning research. And this model is aiming to generate newly data from the learned pace data by using uh, the adversarial training method. So here we have the general diagram of how the model works. First, we give the model a random noise, and the model using the generator will create an image. Now, this image is compared to the real image or the ground truth by the discriminator, and the discriminator will tell whether the image is real or fake. And by doing this, we could optimize the discriminator and the generator loss. So here's how the training work. We will also depth in detail. We will explain in detail in the next session. Okay, so here, before we delve more into how the gun is trained, I want to maybe touch a little about the concept of gun itself. So basically, when we see an image, for example, image of a human or a dog, we could see the similarity between those images because it is possible. There's a probability distribution describing the kind of data we try to generate. So if there's two picture of dog, even the picture is different, we could see both of them is dog. So the research conclude that this kind of pattern is exists in image. So for example, we have the problem of generating a new human face. It's the same problem as generating a new data point that's following the human face probability distribution. Now the problem is we don't know how the face probability distribution is. This is not like the well-defined distribution such as Gaussian or normal distribution. So to generate data from our target distribution, from our random input here, we use the inverse transform method. So we want to approach how the distribution of human face is by using inverse transform method. Once trained, we hope that the generative network can take a random point and transforming it constantly into the distribution that resembles a human face. So here's the generative network diagram. We have input random variables, and ideally we want this network to transform this random variable into a variable that have a probability distribution of human face. And then when we reshape it into the 2D, it will like resemble something that we recognize or understand. Now, the unique thing about the gun is how it's trained. So as we can see here, if we are using a traditional method of like another backpropagation based method, when we have the output of this variable, and if this variable doesn't represent the distribution we are looking, we could do a backpropagation and update the parameter of the network so it could produce a better result. But here, what they propose is they are introducing two networks. So using a generative network to generate a sample and discriminative network to tell apart whether the generated image is a true image or a ground truth image or false. So here, what we have is we input random variable here, and we make the generative network make the distribution, and the discriminative network will check whether that distribution is close or not. If not, it will try to minimize the classification error. while generative network try to maximize the discriminative network. So it's like two network that is adversarial or battling each other to make the whole system better. So if we try to define it, the generator is a neural network that models transform function. It takes an input simple random variable and must return a random variable that follows the target distribution. And while at the same time, discriminator is another neural network that will try to classify or discriminate the output of the generative network. So it takes an input point, and then the probability will be close to true or false. So the goal of generator is to fool the discriminator. So the more better the generator is, the discriminator will not be able to distinguish between the true or generated data. And at first patient, the goal of this discriminator is to detect the fake generated data. So the discriminative neural network is trained to minimize the classification error. So each iteration of the training process, the two of them will be updated in terms of weight, and it will go on until we stop the iteration, or maybe the discriminator cannot tell the difference anymore. This is the illustration of the generator and discriminator. So here, in the initial point, here we have generator trying to generate a distribution of the data. So in the first time, of course, it's not close at all to the original data. And discriminator trying to classify it, because it's also in the first step, it's still not be able to classify it at a good rate. But with each iteration, the generator will try to mimic the probability distribution of the target data, and the discriminator cannot be able to tell it more and more. And finally, in the ideal state, we have the generative model follow the distribution, and the discriminative model cannot tell apart whether it's a true or false distribution. Now we are talking about how to implement this in quantum computing. So the idea of the quantum GAN is similar to classical GAN. We want to have two networks that is playing in adversarial manner. So the first part is generating new data, and the discriminator part is telling whether the data is true or false. So here we have a generator G and a discriminator D. So given a latent factor Z sampled from the strata distribution, generator aims to output the generated data G of the function Z, and probability distribution of G to Z with the probability distribution of G to Z is equal to the original data to fool the discriminator. But unlike the classical GAN, the generator or discriminator in quantum GAN is constructed by quantum circuits. So how we do that is we deploy a quantum device that has n qubits with the O to the this is I think O log n circuit depth, and the feature dimension of the training example is M. So this quantum GAN is proposed by Huang et al. Is using a quantum patch GAN method with the n that is n qubits is less than d log m, consists of the quantum generator and the classical discriminator. So for the full quantum GAN, the discriminator and the generator is in the quantum circuit, but in this approach, only the generator is using quantum circuit. So a potential benefit of this kind of method, it may possess stronger expressive power to fit data distribution compared to the classical generator. Because I think this is the arguments come from the fact that the qubit can fit much more data, so it may possess stronger expressive power to fit data distribution. This is the overall diagram of the proposed quantum GAN. Here we have latent space or input state, and we divide the generator part into several patch here, each generating a specific part of the image, and then later the image is combined. And then the result of this image is fed into the classical discriminator, and it will tell if it's a fake or real. And then from this, we get the loss function, and then we update both the generator and discriminator. Because we just touched how we update the weight or training, next we will see how we get the loss function of this quantum GAN. So as we see in this diagram, for this approach, the generator is composed of several sub-generators. We have a generator T from 1 to the capital T, where each sub-generator refers to parameterized circuit PQC. So here for the circuit implementation, the author uses a PQC. And each of these sub-generator is aiming to output a state where state GTZ, where this state is equal to the ground state or actual data that represents specific portion of the high-dimensional feature vectors. So all sub-generators scale with the O log M operation can either be effectively built on distributed quantum device to train in parallel or on a single quantum device to train in sequence. The generated example is then measured in the last layer, and then it will be fed to the discriminator model. And here we could obtain the loss function to optimize the parameters in the theta and y for generative and discriminative specifically. So here we want to minimize the loss of the generative function and maximize the classification. We want to minimize the generation loss and maximize the loss of the discrimination. So it couldn't tell the difference, and this is the concept of the loss function in this quantum GAN. The concept of patching enables our quantum GAN to complete image generation tests with a large dimension because it's divided into several patches. It will be better if to scale with a larger image. Yeah, so this is maybe just a zoom in version of the quantum patch, how it an illustration. So here we have several several quantum generator patch, each generating different parts of the image. For example, this is a digit 0, so this is just creating the top part, and this is the middle part, and this is the bottom part. So as the author stated, I think the advantage of this kind of approach is because we are using quantum computing, we could run this in parallel. But honestly, for now, I haven't tried how big the advantage is because the simulator we are using for implementation is just still using a sequence operation. So I haven't been able to prove the advantage for this kind of approach yet. Oh, sorry, this is the same slide. So yeah, now here is the implementation of the generator in the circuit. I think it's similar to the autoencoder. We have auxiliary bit qubit here, and we have a data qubit here. So this data is embedded into a state, and then we have a parameter layer here for this. The other use PQC, and this parameter will be updated along with the iteration of the model training. So this one is for sub generator. So if we have 4 sub-generator, we have 4 of this kind of circuit. And the process could be divided into 4 steps. The first one is state embedding. The second one is parameterization. And then we have a nonlinear transformation, and finally post-processing. Okay, so this is example of using quantum GAN. This we tried with the OptiGSat dataset. This is almost the same as MNIST dataset, but it's only 8 by 8 pixel. And to obtain this kind of image, we do a 3000 iteration. So this is the original one. This is the generated one from our code. As we could see, maybe it's not really that similar, but I think it could capture some of the features where there's a curve in the top and there's a line in the bottom. So if you could see this already representing 2 digit 2. And I think our result here is quite in line with the result from the paper. So here's the result from the paper. They use 0 and 1. This is the real data, and the generated is like this. As you can see, the curve is not filled, but it still captures the features of like a blank space in the middle, which like represents 0. But in some cases, there's like unfilled curve, something like that. So I think for this quantum GAN is able to reproduce the feature or maybe the unique feature of the image, but still not be able to produce the image perfectly. This is next one is our attempt to scale this to 28 by 28. So as you can remember, this one is 8 by 8. For the 28 by 28, we use usual MNIST data. And because this is 2828, it will be 784 pixel. We must change how the quantum patch is constructed. So here we have 16 array by 49 generator, which resulted in 784 pixels. And we tried this one with the digit 7, handwriting digit. And this is the result. You can see the difference between each iteration. One thing that I can conclude from this one is that the more pixel it is try to generate, the harder it is to have the consistent like image for reproducing the feature. Maybe as you can see here, like the curve is already resembling 7, but some of the pixel there's some kind of random noise around the pixel. So I think the larger the image, the more this problem will appear. And finally, back to our main subject or main domain, we want to try to apply this into a medical image. And here, what we try to do is the augment process is like this. So we have a medical image, cancer image. We use that is like unbalanced class, and then we use quantum GAN to generate a new image, and then we use that to augment the original dataset. And then for this experiment, we use this dataset. This is the same dataset earlier that has a problem. As you can see, the left one is the original dataset. The right one, we want to make the dataset like this. So the distribution is same for all of the classes after augmentation. And this is the how the train went for the QGAN for these specific cases. This one we tried around 500 iteration, and this is already takes quite a long time. So as you can see here, I think one of the characteristics when training GAN is the generator and discriminator is trying to because it's trying to fool each other. When the discriminator loss is increased, usually the discriminator loss is decreased, and vice versa. Here we see the discriminator loss is uh, decreasing, but the generator is increasing, like that. And here we are trying to do a classification after the augmentation. So we want to see if the data augmentation is really effective or helping in the classification progress. Will it make it better or not? So for the classification, we use just normal CNN. We use a 5-layer for the convolutional and one fully connected layer. And here we use 10K data. We split it so 90% training and 10% testing. And for in this case, we just use a binary classification. So we take this class and this class and do a binary classification. And here is the training progress for the classification itself. First, we use a segmented image. So from the image earlier, we segment it and we use it as the feature. So here we don't use the augmentation first. So here the class is imbalanced. And here we use the augmentation. So here the condition of the class is already equal in the term of size. Now this is the test classification result of the experiment. Maybe I just want to focus here. So in the left part, this is the classification result using the original data as the feature. So we fed the image without any processing, and we fed this in the full size image. I think it's 96 by 96. As you can see, the loss is pretty low. The classification model performs really good. But when we downscale it to 24 by 24, the loss is almost double here. And also when we're using grayscale, the loss is increased quite a bit. Here we are trying to extract the feature by using a segmentation. So this is only using the segmentation of the image. This one is also 24 by 24. Here we have a better loss compared to grayscale, but still not as good as RGB. But here, surprisingly, after we augmented it, so this is the condition where the data is equal. Actually, the loss is increased quite a bit. But if we see the AUC ROC, where we could challenge the capacity of the model to distinguish between two classes, after we do the augmentation, it's getting better. So after augmentation, the model could distinguish between two classes better compared to the without any augmentation. And that's it all for my presentation today, covering the quantum GAN and quantum autoencoder. Maybe next we will move to the demonstration part. Is there something anyone want to ask before we move?
Oh, yes. I'd like to ask about in the GAN the presentation, you talk about the target distribution.
Yes,
So
Professor.
do we have how do you specify the target distribution?
Are you mentioning about the target distribution when we generate an image, Professor?
Yeah.
Oh, yeah. So that is the. Let me go back first. Okay. So, Professor, from what I know, in the GAN, because we want to approach a certain probability distribution, actually we don't know the initial distribution for that image. So, for example, Of course, we know that the distribution between a picture of a human and a picture of a dog is different because as a human we could tell the difference right away. But if we like represent it in the a bit, or maybe we represent it uh, as a probability distribution, we know it's different, but we don't know how it's shaped or how it's distributed. So uh, the concept of the gun itself is how we could make a model that approach that distribution by extracting it from the image. So while we don't know the exact shape of the distribution, we could derive it from the image or from the ground truth. So I think that's how it works, Professor.
Oh, okay, I see. Another question is in one of your slide, you have a formula where big N is related to small letter d times log of m times e.
Let me try to find it. Is it in the gun section, Professor?
Yeah, in the gain section. There's a formula where you state the big N is related to small d times the logarithm of big M times E. So I'd like to know what is the meaning of the small letter d. Is it the depth of the circuit?
Is this one, Professor?
Is it the d stands for the depth of the circuit?
Or the D here?
Small d. I think is it the next?
Oh, this one. Sorry. Oh, this is the same. Oh, wait.
Appears the one.
Oh, this one.
The last paragraph.
Oh, the last paragraph.
N less than d log m e.
Oh, yes. Oh, sorry. I
So what
didn't
is the
explain it.
small letter d denote?
So actually, I think this one is about the quantum. This one is about the patch gun, Professor. So as we can see, because the n is the train feature, we need the n to be less than because the qubit is 2 to the power of n. So the n itself must be less than log m. I
So
think here, yes.
what about the letter d, small letter d?
Oh, that one is, yes, as you said, this is the depth of the circuit.
Circuit. Okay,
Yeah.
got it. Okay, all right. Yes, thank you. Yeah, go ahead and do the demonstration.
Okay, thank you, Professor. Okay. Let me try to share my screen on the Google Colab. Oh, wait. Okay. Could you see this Google Colab page, everyone?
Yes. Mm-hmm.
So first, maybe I will start with the demo of quantum fractional encoder. Yeah, okay. So I think we don't have a GPU quota anymore. So if there's some part that is slow, I will just show you the result because I have saved the result. Okay, so for this implementation, actually, this is we are following from the how the paper implements the autoencoder. And for this one, we are using the Qiskit library. So here's the first cell is just the requirement for the Qiskit. We are using the newest Qiskit and the Qiskit machine learning package. And also this is PyLatex is just prerequisite for the visualizing the circuit. So here, while we wait for the install, maybe I'll explain this part. So this is just the required package for running. JSON is for saving the parameter. We use TensorFlow. So this one is using TensorFlow as the to store the tensor and the image data. Matplotlib is just for visualization, and as usual, this is really essential in many projects. NumPy, Pandas, Seaborn for visualization. Also, Matplotlib is the same. This part is for the image manipulation or processing. We use SK image transform. This one for resizing the image. We use also, there's some method from the OpenCV used. And okay, it's already finished installing, I think. And this part is just import from Qiskit. So we use some circuits here from the Qiskit library. And for the optimizer here, it will be important later. We use Kobila. Kobila is like, I think it's not a gradient-based optimization algorithm. So this is the one that is used for updating the parameter of the network later. Next, we have the real amplitude. This one is to store the values of the image that we want to encode, and other stuff for also storing it in the quantum set, such as set vector. And this is some of the library used for the training, such as the raw feature vector. This is used for transforming the image into the feature vector of the qubit or the circuit. Oh, sorry. I think there's a conflict of the Qiskit here, but I hope it's okay. So here, oh, wait a minute. Oh, I think this is a different notebook. Sorry. Let me fix it. Okay, could you see it now?
Yes, I can
Okay,
see.
I'm sorry. So the previous notebook is actually not for the demo one. That one is for the medical image. So because in this demo we are only using MNIST, it's using a different version of the Qiskit. So yeah, maybe let me go along with the explanation. So after we do import of the library here, next we will create a class of the unitary circuits. Here we are using ansatz, as I have mentioned earlier in the slide. We're using ansatz to store the state. Here is using real amplitudes. So this is just the class definition for that. Okay, this is already finished executing. Execute this one. Now here, we define the autoencoder circuit. So here we are using the quantum register class. Here, how many register we want is the number of latent plus 2 times number of thresh. This is for the thresh plus the reference state. I think we use just multiply it for plus 1 auxiliary qubit. And this is a classical register. This is required for the circuit. And here we compose the circuit from those two above. So we create a quantum circuit by passing two of the parameter above, and then we compose this using the ansatz we defined here. We create the ansatz in the number of the latent and thresh, so the number of qubits we want to input, and we use barrier. So actually, I am not really sure about the use of a barrier, but from what I read, it is required to uh, insulate. Actually, I think it's in the physical implementation is to insulate the quantum computing from the environment. So this is like the barrier to insulate that, and then this is the auxiliary qubit needed. Now this part is the swap test that uh, I mentioned in the slide. So here we could use a circuit H for the swap test using passing auxiliary qubit, and how many swap tests is equal to the number of the trash space we want to discard. So here we just iterate this along the num trash, and we create the swap test circuit here. So here you can see the visualization of the circuit is the same with the one I put in the presentation or slide. Here we have the input and then the swap test. And now for the data set, because I want to save time, this is I create a custom, like a custom test data set. So this is supposed to represent handwriting. So this is just like some pixels where the pixels for several tile is given amplitude bigger than other. So here, as you can see, we do random generation for back for the initial state. So this is like the initial noise, and we insert pixels for each class. So for this one is supposed to represent the digit one. So for this index, we insert value from 0.9 to 1. So as you can see, this one, because it's range from 1.9 to 1, it will much more stronger than this one. So what we get in the end is something like this. So as you can see, the background, this is from the random generator. Some of them is brighter, some of them is not. But in the section we divide, because it's 0.1 to 1, it's really strong. So it makes like a one digit one. And it's also the same for this one is 0. So here in this pixel, we just assign a bigger amplitude. So it represents 0. And finally, I try to make a character 8. So this will be our data that we try to compress. Now here, maybe you realize this is 8 by 4 pixels. So in total, we have 32 pixels, which means that we could represent it in the 5 qubits equals to the power of 5, 32. And here we define, because we have 5 in total, we want to just keep 3 qubits, and we want to discard 2 qubit to trash qubit. So we compress it from 5 qubit to 3 qubit. And this one is the initialization of the vector. So by using this, we create the fresh qubits with the number of 2 to the power of 3 plus 2, so 5. So we initialize 32 bit or 5 fresh qubit, and we initialize the autoencoder here. So we make the autoencoder with the 3 plus 2 qubit, which is 5. And finally, we compose. We make all of them into one, and we get this circuit. So here we have input. This is where the initial parameter is initialized, and this is the amplitudes of the input data. So here's where it's like being converted into the circuit or into the qubit state. And next, this is just a portion for the training. So here we have sample QNN. So what sample QNN here do is to record the weight of the circuit and then do the update later. So this will record or store the weight of the parameterized circuit. Next, we will define the cost function that we will optimize here. Uh, Here, we use the cost function digits as a class, and then we get the probabilities by using the previous QNN. By combining the train image, this is the input image we want to train, and the value of the parameter. We will pass the parameter later, but as I said, in the initial parameter is randomized. And next, after each iteration, we want to plot it as we want to see how the training goes. So this is just the function for plotting the training. Now here's the optimization part. So this one, in the earlier, as I said, we use a Cobila as an optimizer. Here we just will try 10 iteration, but I already saved the parameter for the result of 500 training. So we will use that later for the result. This is just to illustrate how the training is being done. So we try to train it for 10 steps. Yeah, it's already done. So here you can see the objective function is still high, around 0.4, and it's still not still not converged at all. Still not converged. So you can see 10 step is not enough. And here, so here I already have a parameter prepared. So this one is parameter that I get from training it around 500 times, 500 steps. Now we try to encode. So this is quite the long part. First, we have the quantum circuit. So this one is the same circuit we defined last time, but because we already trained it, we now want to use it for decoding. This is the ansatz, same as earlier also, for the storing the amplitude, and this is the rest of the barrier. Now we iterate each image from the dataset we have. So our dataset is 0, 1, and A. We use that and we try to compress them all. Here we assign the parameters of the FM. The FM is the real amplitude for storing. So we store the image to the quantum state, and we represent it in the state vector. So this function is to change it to state vector. This one just record append is to save the data for later visualization. And this one is reshape it into image form again. So 8 by 4. Now for the autoencoder circuit itself is here. So we concatenate the image and the parameter of our trained result. So this parameter and the image is concatenated and it's being set to the quantum circuit. And the quantum circuit will encode the parameter. And finally, we get this output SV. Output SV is the state which is already compressed. This one is so supposed to be 3 qubit after compression. And here we are shaping it to 2 dimension to see the result. So if you run this, you could see we have 3 data. So this one is the input data 1. So as you can see, this is 32 pixel, and this is after the compression. This is 8 bytes. So yeah, 3 qubits 2 to the power of 3. This is become 8 bytes. So this is the compress. This is how after it compress only 8. And after the rest is discarded. So this one is just empty pixels. This is the A. It's compressed to something like this. Next, after we compress, we want to try to decode it. So for the decoder, it's the same. We prepare a quantum circuit with the size of the initial image, because the initial is 5 qubit. We want to decode it back to 5 qubit, so 2 plus 3. And then we compose it. As you can see here, the circuit is just the inverse of the ansatz. So it's just, we could just inverse the encoder and we get the decoder in this implementation. And this is similar to the encoding process. We just iterate through the compressor set. So all of this pixel, we are decoding it back. And the process also similar. We assign the parameter here, but for this one, we assign it to the decoder, not the encoder. And it's the same. We will get the result of the decode here as a state vector, and then we reshape it back into the image form. And here we just show it in the plot. So here's the result. In this plot, we are comparing the original input data and the output data. So here you can see the input data, the output data is quite similar, but here the region here is much more darker. So the amplitude here is lower than the original one. So it's definitely there's a change, there's a loss in the information. But overall, in this example, we can see that we can still retain the shape or the properties. And here also we calculate the fidelity. This is the equation for calculating the fidelity. Here, after we calculate, we can see that it's actually 0.96 fidelity. So it's quite similar to the input data according to the calculation. Here's for the zero. For the zero here, the fidelity is 0.96. So still quite good. And the A here is 0.94. So it's not as good as the other two. You could see here the A is quite striking in this part where it's used in the original data. There's no value here, but here there's some value appearing. And also here, the top part is getting darker. So maybe the reconstruction for this data is not as good as the other two. So yeah, maybe that's the demonstration for the autoencoder.
Okay, yes, thank you, Dr. Andra, for your nice presentation. So, so now we still have time for a couple of questions.
Okay, so yeah, maybe we could directly go to question, Professor.
Yeah. Mm-hmm. Is any question from the audience? Okay, so let me ask one question first. I remember in your comparison for the performance between the CNN and the quantum autoencoder for different pathological image, whatever is historical or skin or blood.
Yes.
So it looks like the quantum encoder does not perform as well as the CNN. Did you optimize both the CNN, also optimize your quantum encoder when you make the comparison?
Okay, Professor, thank you for the question. Do you mean this one, the quantum CNN?
Yes, yes. Did you optimize the one, say, CNN and QCNN or VQC? Optimize the so-called hyperparameter optimization, and in the quantum part, you might have to optimize the entanglement or or how many repetition for the circuit depth. Yeah, otherwise it will be unfair to make the comparison if you do not optimize each one of it and make the comparison.
Okay. Yes, thank you, Professor. It's a really great question. So actually, as you mentioned in this table, this is like the table that I share with my college for the progress meeting. This quantum CNN is not really optimized. So as you can see here, I made the note. This is a 16 by 16, right? So the reason of this is because for the rest of the method, I use 24 by 24, but for the quantum CNN, because the training takes so long, I cannot get it done. And finally, what I do is I resize the image to 16 by 16, and then I finally the CNN is I could get the result from CNN. So by itself is as you mentioned is already not fair because this is just this use a lower resolution image. I just want to test how the QCNN at this point. So this is actually not optimized at all, Professor. And for the, I think for the quantum CNN, the depth is only like 3 or 4 layers. So I think there's a lot of space to optimize this for this QCNN and VQC. And for PQC, relative to the QCNN, I think the result is much better. But this kernel for the PQC, I think the kernel is optimized. But I forget how many steps does it take for the PQC to get this good. But what I remember is that the PQC at least doesn't take as long as QCNN. So yeah, the QCNN here is really in the experimental phase, and it's just the result is not good at all.
Oh, okay, I see what you said. So, I mean, in order to be fair, and I do understand the limitation of this QCNN. Then is it that will be much fair if you use a 16 times 16 for SVM, CNN, and VQC, and then make the comparison? That would be a more fair comparison, right?
Oh yeah, I think so, Professor. But yeah, at this point, I haven't tried to resize for the rest of this. So yeah, as you said, this one is still, and it's not a really good comparison for data. Maybe next time I will try to resize it to the same amount for comparison. So actually, for the actual data, we only take these 3 stops. So CNN actually it's not really that. I mean, it's not really considered for our research data. This one is just for curiosity. But as you said, I think it's much more fair to resize it to 16 by 16 first, and then we could from there we could compare the performance between this method. Thank you very much.
Yeah. Okay. All right. So let's see if any other question from the audience. Okay, looks like we do not receive any response from the audience. Okay, then I think there will be a time we can close this section. So thank you again, Dr. Andra, for your very nice demonstration and the presentation. Thank you.
Thank you very much, Professor. Thank you for giving
Yeah.
me time.
Okay, all right. Then bye. Bye, everyone.
Thank you for today's talk. Thank you, Dr. Lopez.
Thank you, Professor.
Yeah. Okay, all right. Hey.